Hello everyone and welcome back to tutorial 8 of MIE100, the dynamics course at the University of Toronto. My name is Noor and today we're going to talk about dynamics of rigid bodies, specifically plane of kinematics of rigid bodies. We're going to be doing 3 questions where I'm going to be explaining how those dynamics of rigid bodies come to play. So stick around, and if you have any questions, leave it in the comments below. Okay, so we're starting off with problem 1. By the method of this article, determine the angular velocity of length AB and the velocity of color B for the instant represented. Assume the quantities omega naught and r to be known. Okay, so let's take a closer look at this picture. We've got the angular velocity going this way, and the color at B is going to be moving this way in that case. So this is going to be VB. And VA, because this whole wheel is moving this way, so VA is going to be pointing in this direction over here. Okay, so we want to find the instant center of rotation. Where is the center of rotation for A and B? We're going to extend this a little bit out. So we know that the angle here is 45 degrees. And the angle here is 30 degrees. So this point over here, let's call it, for example, C, is going to be our instant center of rotation. Because we want to isolate member A and B. You want to isolate this link and find the center of rotation for this link. So now we're going to start solving. We've got our vector rotation equations. And we know that v, the velocity, is equal to the angular velocity times the radius. So that means that VA is equal to omega naught times r. Now, for some relative motion, we want to know omega AB, right? And we know that the center of rotation is going to be C, so we want to find the angular velocity of the link in terms of VAC, right? So VAC is going to be equal to VA minus VC. But because C is just the center of rotation, and it's a fixed point, it's going to be equal to 0. So now that we know what we need to find, we need to calculate this guy over here, this distance over here. So we're going to go back to our trigonometry and geometry equations, and we're going to find the angle here. So 180 minus 45 minus 30 is going to give us 105. So now we're going to have sine 105 over the length of link AB is going to be equal to sine 45 over the distance BC, which is also equal to sine 30 over the length of AC. Now we're concerned about AC now. So we're going to plug in our known values. AB, we know, is equal to 2r. So 2r sine 30 over sine 105 is going to give us a length of 1.035 r. And when we plug that into our equation over here, we can get omega naught r, because that's what VA is equal to. Remember, VAC is just equal to VA because VC is 0. So we're going to plug in this equation over here. Over 1.035 r. That's going to give us an angular velocity of the link AB is equal to 0.966 omega naught in this direction, in the positive direction. Sorry, no, in the negative direction. Yeah. Okay. Now we want to find VB, the velocity of color B. So omega AB is also equal to VBC over RCB. And from our relative equations, for our relative motion equations, we know that VBC is going to be equal to VB minus VC, where VC is 0 again. So it's just going to be equal to VB. Now we're going to try to find this guy over here. And from our equations over here, we know that BC is going to be equal to AB sine 45 over sine 105 to give us 2r sine 45 sine 105. BC will finally equal to 1.464 r. And once we plug that into our equation over here, we get 0.966 is equal to VB over 1.464 r, which will give us a value for the velocity of color B equal to 1.414 r omega naught. And that's our final answer here. So now for our second question. The center C of the smaller wheel has a velocity Vc of 0.5 meters per second in the direction shown. The cord which connects the two wheels is securely wrapped around the respective peripheries and does not slip. Calculate the velocity of point D, when in the position shown. Also compute the change in delta x, which occurs per second, if Vc is constant. Okay. So we want to find Vd, and we want to find delta x per time, which means x dot, correct? So first of all, we're going to look at this ball over here, or this wheel over here, the center C. Now, Vc is going this way, and since Vc has a velocity, then C cannot be the center of rotation. Center of rotation has to be a fixed point. And because it's turning on the ground, this point over here at this instant is going to be 0. And therefore, is going to be the center of rotation. So the distance from the ground to C is R, and from the ground to A is 2R. Now that we've established that, we can fairly say that the velocity of A is going to be equal to 2VC. And since A and B are connected by a cable here, or by a cord, we can also confidently say that VA is going to be equal to VB. Now, for our vector rotation equations, we know that VB is going to be equal to angular velocity over the radius. So for VB over here, to find the radius, we're going to take a look at the ball. So this is the bigger ball. That's B over here. And that's center O. That's the instant center of rotation. So from there to O, from the ground to O, it's going to be 100 millimeters, so 0.1 meters. And from O to B, it's going to be 200 millimeters, so 0.2 meters. That means that from the ground, the instant of center rotation, to B, it's going to be 300 millimeters. And now we've got RB. So 2 times BC, which is 0.4 meters per second, is equal to omega B over 0.2 plus 0.1 meters. And that's going to give us the angular velocity of B, which is 2.667 radians per second. Okay, now, now we want to find the velocity of O. So V naught is going to be equal to omega B again, because the angular velocity of B and O are going to be the same. Multiplied by radius O. And that's going to give us 0.267 meters per second. And because, remember, we want to find VD over here, we can now relate VD with VO using the relative motion equations. So VDO is going to be equal to VD minus VO. And now to find VDO is going to be equal to omega B, because the angular velocity is going to be the same in the entire ball, or in the entire wheel. Cross product RDO. It's in the K direction, and this is going to be in the J direction. And we're going to plug in our known values, so that's center The distance from here to here is 0.2 meters. And that will give us a value of 0.533 meters per second in the j direction. And once we've done our cross product successfully, we can then find VD to be equal to VDO, which is 0.533J, plus V naught, which is 0.267I. So that's our answer in x and y coordinates. But if you want the scalar velocity, D, we're going to put our i's and j's under the square root. So 0.267 squared plus 0.533 squared, all under the square root to give us scalar velocity of D equal to 0.569 meters per second. And now we also want to find x dot, or delta x over t. And this is just going to be equal to the velocity of O relative to c. So because the distance between O and c is basically x, we know that the velocity of O relative to c is going to be equal to x dot. So let's write that down over here. X dot is going to be equal to V O with respect to c. So using our relative motion equations, we know that this is going to be equal to Vc minus Vo. And since we already know the values for these, we're going to plug them in, and we're going to have 0.4i minus 0.267i to give us a final answer of 0.133i meters per second. And for our final problem, in the mechanism shown, the initial velocity of point D is 1 meters per second in the I direction, and the initial angular acceleration, ACD, of bore CD is minus 5 radians per second squared. So we've got 4 parts for the question. We'll start with A. What is the initial velocity of point B expressed in x and y coordinates? All right, so we know that VD is 1 meters per second in the I direction, and the acceleration alpha CD is equal to minus 5 radians per second squared. And we want to find VB in x and y coordinates. So first of all, we're going to use our relative motion to find VB. So VBC is equal to VB minus VC. However, C here is a fixed point. Therefore, it's the center of rotation, so it's going to be equal to 0. And VDC is going to be equal to VD minus VC, which is also equal to 0 for the same reason. So VDC is just equal to VD, which is equal to 1 meters per second in the I direction. And now we're going to use the vector rotation equations. So for VDC, we know that the angular velocity cross product with the radius, or the length to the center of rotation. And once we plug in our known values and do the cross product, we know that 1I is going to be equal to minus 0.18 omega dc I. So that's going to give us the value for the angular velocity of dc, which is minus 5.56 radians per second in the k direction. Now we're going to do the same thing with VB. VBC is going to be equal to omega BC cross product of B relative to C. And once we do that, we know that omega BC is equal to omega DC, because it's all in the same link. That means they all have the same angular velocity. Therefore, we're going to sub in our known values. Which is VBC, which is equal to VB, is going to be equal to minus 5.56 radians per second. Okay, cross product 0.12 meters J, to give us a value for the velocity of B equal to 0.667 meters per second in the I direction. Now that we've done part I successfully, let's take a look at part B. And part B is asking for the acceleration of point D expressed in normal and tangential coordinates. B is asking for AD, normal and tangential coordinates. So again, using our relative motion equations, we know that ADC is going to be equal to AD minus AC. And AC is going to be equal to 0 because VC is 0. And let's try to remember our normal and tangential coordinates, how they look like. This is the rod D and C, and this is the acceleration. We know that the normal acceleration is going to be pointing towards the center of rotation, and AT is going to be pointing towards the angular velocity or angular acceleration. Therefore, AD is going to be equal to negative AN negative AT. Oh, sorry. This is not negative. This is in the positive direction. So, going back to our vector rotation equations, we have to recall our acceleration equations. We know that V is equal to omega r, but we also know that the acceleration in the normal direction is equal to omega squared cross product r, and the tangential acceleration is equal to the scalar acceleration cross product r. So these two are what we're going to be using for this part of the problem. And we're going to plug them into our equation, into this equation over here. So AD is equal to minus AN, which is minus DC squared cross product RCD plus alpha DC cross product RCD, and we plug in our known values. So this is going to be minus 5.56 squared cross product 0.18J plus minus 5K cross product 0.18J. And finally, we're going to be left with minus 5.56J plus 0.9I. And if we express that in normal and tangential coordinates, it's going to be 0.9 UT plus 5.56 UN. Okay. Now let's go to part C and D. We've got C asking for the initial velocity of point A expressed in Cartesian coordinates. And we're going to actually be doing part C and D together. So we're going to be doing those two parts together because they're very intertwined. And we're also going to find the initial angular velocity of bar AB. So here we want VA in Cartesian coordinates. And the angular velocity of AB. Now to solve this, we're going to be using the relative motion again. VAO is going to be equal to VA minus VL, and VAB is going to be equal to VA minus VB. Using the vector rotation about a fixed axis equations, we're going to sub in this guy over here with omega AO, cross product radius of O with respect to A is going to be equal to VA minus VO. However, we know VO is going to be 0 because it's the center of rotation. And we're going to do the same thing with this guy over here. Cross product of radius of B with respect to A, VA minus is equal to VA minus VP. And then we're going to plug in our known values. So we know that this is going to be equal to 0.08I, this guy over here. Is going to be equal to VA. And once we do the cross product, we're going to get 0.08 omega AO J is equal to VA. So we know that VA is also going to be in the J direction. And now we're going to plug in our known values in this equation. RBA is going to be the distance from here to here. So this is going to be in the X and this is going to be in the Y. And that will give us 0 0.16i minus 0.12j equal to VA minus VB, which we found earlier, equal to 0.67i. We know that VA is in the J direction. So once we do the cross product here, we're going to get 0.12 omega AB in the I direction plus 0.16 omega AB in the J direction equal to VAJ minus 0.67I and since we know since we can already solve for this over here, we're going to isolate I to get 0.12 omega AB in the I direction is going to be equal to minus 0.67, also in the I direction, to give us the angular velocity of link AB equal to minus 5.56 radians per second. And that's the answer for part D, actually. And now that we've got the angular velocity, we can easily sub that in to this equation over here, where we isolate J to get 0.16 multiplied by minus 5.56 in the J direction is equal to VAJ to give us the answer for the velocity of A equal to minus 0.89 meters per second in the J direction. That's the end of our questions. And that was the end of our tutorial. Thank you so much for watching. If you have any questions, feel free to email me at noor.doidar@mail.tutorano.ca or leave your question in the comments below. Thank you and see you next week.